Hi, welcome to 2022 Milan No-Till Field Day Tour for Climate Smart Agriculture. My name is Debasish Saha. I am an assistant professor in Biosystem Engineering and Soil Science Department. Today, I would like to share some of our research in understanding cover crops' role in mitigating greenhouse gas emissions, in particular nitrous oxide emissions from soil wetting and drying, which simulates natural precipitation variability. Climate smart agriculture is probably the word that you are hearing these days a lot. And this is an important topic with regards to reducing greenhouse gas emissions. Our atmosphere is accumulating greenhouse gases at a much faster rate than previously recorded. On the right-hand side, so here you see the historical changes in greenhouse gas emissions from terrestrial environment, and two vertical axes there, CO2, that is carbon dioxide, methane, and nitrous oxide concentration. And you can see early 1900 century, the concentrations started to increase very rapidly, and it is still continuing to increase in our atmosphere. And that was mostly due to industrial revolution, application of fertilizer in agricultural fields, transportation, etc. So climate smart agriculture is mainly intended to improve the environmental sustainability of agricultural industry by helping to reduce atmospheric greenhouse gases. And this is important because there is rising demand for sustainable food and non-food products. And due to that reason, both public and private sectors are setting their targets to achieve, net zero or zero emission goals by 2030, 2040, or 2050. So to achieve that goal, we need to understand what are the climate smart practices and how they can contribute to mitigate greenhouse gases. For example, conservation management practices like no-till, cover cropping, nitrogen fertilizer management, which producers have been doing for a long time, and they can be important tools to achieve such goals in reducing greenhouse gas emissions. Now, how climate smart agriculture and increasing weather variability they interact. All climate models unanimously they predict that more intense drought and greater precipitation variabilities are expected in the coming years, or we are already experiencing that. And drought has an important impact on soil carbon and nitrogen cycling. For example, here, if you look at the bottom left demonstration here, so here is a cotton crop growing, and there is an in-season drought that reduced the water uptake by the plants and the plant growth. And similarly, when the plants are not taking up water, they are taking less nutrient from the soil. So that's why it indicates by the negative sign. And due to that, the soil nutrients, for example, carbon and nitrogen, they tend to accumulate because there is reduced plant demand. And when the rewetting starts due to intense storm event after the drying period, that accumulated carbon and nitrogen could contribute to losses, such as nitrous oxide is one of the possible pathways. It can be leaching too, which is a greenhouse gas, and it is Also detrimental for stratospheric ozone layer depletion, and that has negative consequences on both plant health and human health. So as you can see here that the interactions can be very complicated. And that's why understanding how drying and rewetting influences soil carbon nitrogen cycling and greenhouse gas emissions is important. So rewetting after drought, as I said, can increase the carbon nitrogen substrate availability and trigger potent greenhouse gas emissions like nitrous oxide. And limited is known about how our agricultural aspirational agricultural management practices like cover cropping or no tillage, they can help mitigating such losses when the rewetting happens following a drying period. So nitrous oxide is important greenhouse gas from agricultural sector. The reason is that it is 300 times more important than carbon dioxide. So in terms of mass, the amount of N2O lost from the soil may be much less than CO2, but because it's 300 times more important, that actually makes it very critical component in terms of when you think about the carbon equivalent emissions from the whole system. And mitigating N2O due to that high impact, it could provide the greatest carbon credit benefits in subtropical humid environment. So carbon credit is another term that you probably have heard from different extension events, and it's a potential market opportunities for producers to account for greenhouse gas savings by following aspirational management practices. And if you can reduce nitrous oxide emissions, which has a high impact on the carbon equivalent emissions, then you can claim higher carbon credit for your management practices. And that is also very important because carbon credit also accounts for carbon sequestration rate, which is very low in our environment in Tennessee because of very high rate of decomposition and very little accumulation of carbon in the soil. So N2O could be, reducing N2O could be a low hanging fruit to participate in carbon market. And agricultural sector is very important to target for N2O mitigation because it is the large amount of emissions is coming from that sector because of nitrogen fertilizer. So the right hand side, you can see different sectors and their emission contribution for nitrous oxide based on EPA data. And this big section here, which is agricultural soil management, that is fertilizer management, manure management, tillage management, and that contributes approximately 80% of the total emissions. So it is really important. So agriculture is the largest contributor. That's why if we can target it and if we can mitigate agricultural emissions, we can harness the greatest benefits. So with that background, our research questions were how rewetting drying intensity influence N2O emissions, and to what extent cover crops can mitigate N2O emissions under rewetting drying condition. To address those questions, we conducted a laboratory incubation study for that extended for several months. And in the incubation study, we simulated wetting and drying cycles in the lab environment and measured greenhouse gas emissions from the soil, reconstructed soil cores. Soil samples were collected from 40-year-old long-term continuous cotton experiment in West Tennessee, Jackson. And the disturbed soil samples were repacked into cores like the one that you see in this picture on the right-hand side, top picture. And we had 3 input treatments. One is urea at a rate of 100 kilogram nitrogen per hectare. Second is urea plus crimson clover residue that simulates the crimson clover as a winter cover crop grown after cotton harvest, and urea plus winter wheat as a cover crop grown after cotton harvest. And then we impose 4 different wetting drying treatments. So moderate wetting after extreme drying, moderate wetting after moderate drying, extreme wetting after extreme drying, and extreme wetting after moderate drying. So what does it mean? So moderate wetting is the soil is not saturated. It's something that a predefined moisture condition that you can relate something like 1 or 2 days after the soil achieves fill capacity. And extreme wetting is when the soil is saturated and you can see the water in the soil by the shining face of the soil. And extreme drying and moderate drying. Moderate drying is soil has moisture, but it is drying, and the extreme drying is when there is no rain for 3-4 weeks and soil is extremely drying, and you see visible symptoms for plant wilting. So some data. So here, this table shows the rewetting drying intensity, the 4 different indices that I just explained, and the cover crop treatments within each rewetting drying intensity. And here is the cumulative nitrous oxide emission during that period of incubation. So the numbers may not be of important for this purpose, and the units also, but important thing is to understand the trend, which one is reduced emission or which one increased emission. So under moderate wetting, both from extreme drying or moderate drying, we can see that in both cases, when urea and legume cover crop, which is crimson clover, they produce slightly higher emissions than the no cover crop treatment or winter wheat treatment. However, the interesting trend happened. We could observe substantially higher emissions when the soils were extremely wetted, that is saturated, under when there was no cover crop. For example, in this case, urea, which is almost 2 times higher emissions than the urea plus clover treatment, and almost 6 to 7 times higher emissions from the urea plus winter wheat treatment, and similar for this particular case too. So cover crops in general mitigated 30 to 80% of N2 emissions when the drying process followed by extreme wetting that led to soil saturation. And it is important to note that because the extreme wetting conditions are the one when we can expect higher nitrous oxide emissions when the soil is wet and there is lack of oxygen diffusion into the soil. The presence of legume cover crop residues increase emission under moderate wetting, but decreased emission from no cover crop treatment under extreme wetting conditions. However, the grass cover crop, which is the winter wheat, it consistently decreased N2 emissions irrespective of wetting, drying intensity. So we also wanted to know how the magnitude of change in soil moisture impacts the emission following wetting drying. And in this figure, the horizontal axis, there are no numbers, just to make it simple for understanding. This is change in soil moisture when a dry soil gets wet. That means if you have a dry soil and there is a precipitation, so how much precipitation you get and how much, what is the change in soil moisture because of the precipitation. So on the left-hand side, you have the small change in soil moisture. On the right-hand, as you go to the right, is large increase in soil moisture. That means this part is actually reflects a small precipitation event following drying. And on the right-hand side, there is a large precipitation event after a drying period, like a storm after a drying period that produced like several inches of rainfall in a very short period of time. And the vertical axis is the nitrous oxide emission. And three colors represent three treatments. One is the urea, that is the no cover crop treatment, urea plus crimson clover, and urea plus winter wheat. So there are some variability here, more than what we expected, but in general, you can see a linear trend for N2 emission with increasing magnitude of change in soil moisture during the soil's transition from dry state to wet state. That means larger rain event after a dry period will produce more N2 emission. And interesting finding here is that the winter cover crop, they kind of lowered or irresponsive to this change in soil moisture and reduce N2 emission irrespective of that magnitude of soil moisture change following rewetting. So the take-home messages are frequent rewetting drying under a variable precipitation distribution may increase N2 emissions from agricultural soils. Incorporating cover crops can be an important management when we expect variable soil moisture in reducing N2 emission. However, that magnitude can vary with cover crop species and wetting intensity. As we have seen that under moderate wetting, the legume cover crops tend to increase emissions because the legume cover crop comes with added nitrogen through their residues. So in that case, maybe managing the nitrogen fertilizer application rate can help to mitigate that extra losses. However, the grass cover crops, they provide blanket N2 mitigation throughout different rewetting drying intensities. One thing we should be careful about the grass cover crops because they tend to immobilize the nitrogen in their residue during the decomposition process. So if we have grass residue and incorporating nitrogen fertilizer, so nitrogen limitation to the cash crop must be considered and nitrogen rate should be adjusted accordingly. So variable nitrogen management based on cover crop species composition can balance yield and environmental outcomes under variable precipitation distribution. Again, the findings from this study should be carefully extrapolated because this is based on a laboratory scale controlled study, and field scale evaluation is warranted for further validation of these findings. And we are already working in one of our projects in the field in Jackson, where we are measuring nitrous oxide emissions and other greenhouse gases from in response to long-term tillage, cover crop, and fertilizer management. And hopefully by 2024 no-till field day, we will have some findings to share with you. With that, thank you very much for your attention, and please feel free to reach out to me at this email address if you have any questions or would like to know more about our research.